Hi, and welcome to Lecture 16. This should be Lecture 15B, but it's 16 because, well, it's complicated. I forgot that we had no lecture for the second part of the chain rule, and so I got my numbers out of sync with each other with the lectures and the videos. So this should put us back in sync if I calculated correctly. In any case, we're talking still about implicit differentiation. But this time I'm looking at a few new examples, and all of these examples have to do with the inverse trig functions. I know everyone's favorite friend. Anyway, we will look at how to calculate the derivatives of these inverse trig functions. So in particular, inverse sine, inverse cosine, inverse tangent, and those are the only ones I'm going to do, and I'll explain why in a few minutes. So let's start with the first one, the inverse sine. So the inverse sine you could think of as a function, y equals the inverse sine of x. And I want to know what is dy dx. Now dy dx is getting a little bit cumbersome to write, so I'm going to stick to y prime most of the time when I'm doing this, at least for now. So I want to calculate y prime. Well, the problem is I don't have any idea at this point. We don't have any idea what the inverse of this could be. We could appeal to the definition, which would mean that we'd write the limit as h goes to 0 of inverse sine of x plus h minus inverse sine of x over h. But then we don't have any identities to deal with inverse sine of x plus h. So there's not much we can do with that. Neither can we do inverse sine of x minus inverse sine of a over x minus a. There's not much you can do with that. We don't have any algebra that works on junk like this. So we have to come up with some other approach. And it turns out that implicit differentiation does the job. If you remember what the inverse function means, it's the function that undoes the function that's mentioned here. So the inverse sine is the function that undoes the sine function. So what if we start with this equation and hit it on both sides with the sine? In other words, the sine of y on the left would be the sine of the inverse sine of x. And the whole idea is that sine of inverse sine are matter and antimatter. They cancel each other out. That's the whole reason for doing this, and so we're left with x. So we have this new equation, sine y equals x, which is an equation which relates x and y. So I can go after the problem of finding the derivative of y with respect to x by implicit differentiation on this equation. So I'm going to take the derivative of both sides with respect to x. That's what I'm doing. And I'm going to start with the right side because that's easy. The derivative of x is 1. Now remember, we're taking derivatives with respect to x. So what is the derivative of sine of y? We have to remember that y is not x. Y is some horrible complicated function of x, which I actually know in this case, but it's no help in calculating the derivative. Anyway, it's the sine of y that I'm differentiating. So what is the derivative of sine of anything? Well, we know that. That's cosine of whatever. But the chain rule comes along and says, oh, you got to multiply by the derivative of what's inside y. In other words, the derivative of this. Well, let me write that equation again. Cosine y times dy dx, or y prime, equals 1. Well, folks, here's an equation for y prime. I can solve that equation pretty easily for y prime. Y prime equals 1 over cosine y. And you could say you're done, because this is an answer for what the derivative of the inverse sine is. The only trouble is that this is given back in terms of y. And that's not what you want, because the original question gave you y as a function of x, so you would like to know what the derivative of y is as a function of x, not as a function of y. But that's no problem, because we could just plug in what y is equal to, so you get the cosine of what? What's y? Y is the inverse sine of x, so it's the cosine of the inverse sine of x. Remember, the inverse sine does not mean 1 over sine. It's the inverse function. Okay, well, this is a perfectly good answer, but actually we would like something a little bit better than that. And it turns out there are a couple of ways that you can do this. You can use trig identities, which is what the book does. But I'm going to do it a different way because it's a little bit more intuitive. You don't have to remember many identities, and it also sets up something that we're going to find useful, you're going to find useful in calculus too. So there's another way of looking at simplifying this. What I'm talking about simplifying is whenever you have a trig function applied to an inverse trig function, there's always another way to rewrite this. I won't say it's simpler, but it's different and much more useful than what you see here. This doesn't come up too often. But when we simplify this, when we rewrite this, you will see that it turns into something that comes up a lot. So how do we simplify this? How do we rewrite it? Well, there's a geometric trick, if you like, that helps us deal with this. So it'll be a little involved. About the third time you see this, it may start making some sense to you. But I'm going to start with this equation, sine of y equals x. And I'm going to take that equation and look at it geometrically as if it were on a right triangle. So I'm going to start by drawing a right triangle. Right? So there's a right triangle, and I want to make the sine of y equal to x on this triangle. Well, the sine of y must be an angle then, so I'm going to measure the angle y this way. This will be a right angle, of course. And I want to make the sine of y equal to x. Well, what's the sine? The definition of the sine, if you remember from right triangle trigonometry, is the opposite over the hypotenuse. So I want to make the opposite to y over the hypotenuse equal to x. And I want to do it in the easiest possible way. Well, the easiest possible way that I can think of is to put x here and put 1 there. Then the sine of y is going to be x over 1. And that's what I got, opposite over hypotenuse, sine of y. If I do that, the third side then becomes determined by the Pythagorean theorem. So whatever I put here, squared plus x squared, has to add up to 1. Now, we'll do the algebra just once here in the upper right corner. So I don't know what that thing is, so let's give it a name. Let's call it u for unknown. But whatever u is, u squared plus x squared has to add up to be 1 squared according to the Pythagorean theorem. So if I solve for u, I get u squared equals 1 minus x squared, and so u equals plus or minus the square root of 1 minus x squared. I'm going to take the plus square root. So u is, I'm going to scratch through that because I don't need u anymore. It's the square root of 1 minus x squared. So that is the remaining side. And now the neat thing about this is once I've figured out everything on this triangle, I can read this part right off the triangle, because what was inverse sine of x? Inverse sine of x was y. And I'm looking at cosine y. That's no surprise, we were using that earlier. So if I look at this as 1 over cosine y, I can just read cosine y off of here. Cosine is adjacent over hypotenuse, just like sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So this becomes, cosine is just the square root of 1 minus x squared. So this becomes 1 over the square root of 1 minus x squared. And that is the derivative of the inverse sine. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. And this expression does come up a lot. All right, let's do another one. What about the derivative of the inverse tangent? One of my favorite functions. Well, I don't know, so we say let y equal the inverse tangent of x, and then undo the tangent by taking the tangent of both sides. So tangent of y must be equal to tangent of inverse tangent of x, and of course that's going to cancel the inverse tangent and leave you with that, just x. Okay, so now I have an equation that has x and y in it, so I can hit both sides of that equation with a derivative, differentiate both sides with respect to the independent variable x. Again, I'm going to take the derivative of the easy part first. The derivative of x, that's 1. Hope everybody's got that. Now, the derivative of tangent. Well, you have to remember that the derivative of tangent is secant squared. Derivative of tangent is secant squared of what? Secant squared of y, because that's what we got here. Are we done? Well, no, because remember we were taking derivatives with respect to x, not with respect to y. So what's y? Y is this horribly complicated function of x. So how do I take the derivative of tangent of a function? Answer is the chain rule. Chain rule says go ahead and take the derivative of tangent. You get secant squared. Plug in whatever's there, which is y, but you got to pay the price. Multiply by the derivative of what's inside, the derivative of y. And we've done this. This is what we were doing the last couple of days with implicit differentiation. So this gives us a formula, real quick. Y prime equals 1 over secant squared of y. And you could say, well, I could substitute in now y equals inverse tangent, and I've got secant squared of inverse tangent of x, which is a good formula, but I can do a little bit better. Let's build a triangle here and make this equation happen on that triangle. So again, our angle is y because I'm taking the tangent of it. So I'll put y down here, and I want to make the tangent of y equal to x. Well, you have to remember what the tangent is in triangle trigonometry. The tangent is the opposite over the adjacent. So here we go, opposite over adjacent. I got to make that equal to x. Again, that's not too hard. The easiest way to do that is to put x here and 1 there. Opposite over adjacent is tangent. Opposite over adjacent will be x on this picture. Now I got to figure out what the remaining side is, and the Pythagorean theorem again tells me how to do that. Whatever I put here has to be squared and equal to the square of x and the square of 1. So what I have to put here, I have no choice, has to be the square root of x squared plus 1. X squared plus 1 squared, of course. Check it. Square this, square x, square 1, add these together and see that you get the square of that. And you do. Okay, so what is this? What is this derivative of y? What is the derivative of the inverse tangent? It's 1 over the secant squared. Well, I have to read off what the secant is, because remember, secant squared means secant of whatever quantity squared. So what is the secant? The secant is 1 over the cosine. So the cosine is the adjacent over the hypotenuse. So the secant must be the hypotenuse over the adjacent. And so hypotenuse over adjacent would be square root of x squared divided by 1. That's easy, square root of x squared plus 1. So secant is just going to be square root of x squared plus 1. And then that thing is squared, so guess what? It's actually not too bad. 1 over x squared plus 1. Or, if you prefer, 1 over 1 plus x squared. Same thing, obviously. One over 1 plus x squared, 1 over x squared plus 1, whichever one you prefer. But this is the derivative of the inverse tangent. Okay? Very, very important. This comes up all the time. All right, the last one I'm going to do is the derivative of the inverse secant. What is the derivative with respect to x of the inverse secant? Well, I don't know, so we let y equal the inverse secant of x, and then hit both sides with the function that kills that inverse. So, of course, that would be secant. So secant of y equals secant of inverse secant. That's going to kill it, leaving me with x. Been here before. We're going to take the derivative of both sides with respect to the independent variable, x. So on the right, we get the derivative of x. That's 1. On the left, what's the derivative of secant of anything? The answer is the secant of that anything times the tangent of that anything. Derivative of secant is secant tangent. But that thing there is not the independent variable. It's a function. It's this complicated function of x. So the chain rule says, you got to multiply by the derivative of what's inside. So out pops the derivative of y, which coincidentally is what you're looking for. You want to find dy dx, y prime, the derivative of the inverse secant. So here it is. You found it. Y prime equals 1 over secant y tangent y, which of course is a decent answer. Whoops, tangent y, except that it's got y's in it. So you could substitute back in inverse secant. Oh, in fact, we could do that right here. See? Let me scroll this down a little bit. I can substitute in at least one. Well, we'll do it both places. I don't care. This is secant of y, and y right here is inverse secant. Inverse secant of x times tangent of inverse secant of x, just by substitution. And everybody knows that secant of inverse secant cancels because they're inverses, so you're just left with x, times, now you got to work this thing. What is the tangent of the inverse secant of x? And as I said, anytime you compose a trig function, like tangent, with an inverse trig function, you're going to be able to write that in some other way. You could do this with a trig identity, and that's what the book does, but we will use our triangle again. So here's our right triangle, and what I've got to do is make our equation, this guy, secant of y equal to x, make that happen on this triangle. So again, our angle is going to be y, and I want to make the secant of y equal to x. I have to remember what the secant is. The secant is 1 over the cosine is the adjacent over the hypotenuse, so this must be hypotenuse over adjacent. So I've got to make the hypotenuse over the adjacent equal to x. Well, it looks like the only way that's simple to do that is to put x on the hypotenuse and 1 there. So hypotenuse over adjacent is certainly 1, x over 1, and that means I've got to figure out what this side is. So if you pull the Pythagorean theorem out and solve for this unknown side, here's what you'll get. Square root of x squared minus 1. Don't believe me? Square this, you get x squared. Square these two guys and add them together. 1 squared plus this squared, this loses the radical when you square it, so you get x squared minus 1 plus 1, the 1's cancel, you're left with x squared, which is the square of the hypotenuse. So yeah, this is the remaining side. So now, we can read off from here what the tangent of y is, because y, remember, y is the inverse secant, so this is the tangent of y, right from there. Right? This is the tangent of y that we're trying to figure out. So this is going to be 1 over, and this x is still there, but what is the tangent of y? Well, we just read it off. Tangent is opposite over adjacent, so that's going to be square root of x squared minus 1. And that's it. That is the formula for the derivative of the inverse secant. 1 over x, square root of x squared minus 1, which isn't real pretty, but it's different, and it's not necessarily what you might have expected. Here's the derivative of inverse tangent, 1 over 1 plus x squared, or 1 over x squared plus 1, and here's the derivative of the inverse sine, 1 over the square root of 1 minus x squared. Now I want to summarize these and add in the other 3 inverse trig functions. And I'm going to build a little table like I did with the derivatives of the trig functions when we did that a couple of weeks ago. But I'm going to do it again differently from the way the book does it. I can't believe the book did it this way. That's really, really dumb, the way they did it. We're going to do it in a way that makes perfect sense. I'm going to write the derivatives of the 3 that I found on the left. The derivative of the inverse sine, the derivative of the inverse tangent, and the derivative of the inverse secant. And the answers are, to just summarize, this is 1 over the square root of 1 minus x squared. The derivative of the inverse tangent is 1 over the square root of 1, no square roots in this, 1 plus x squared. And this guy, the last one that we did, we're still looking at it right there. It's 1 over x square root of x squared minus 1. It's a little bit hard to remember because this has a square root of x squared minus 1. Inverse sine has a square root of 1 minus x squared. So I suppose you might remember it because sine and tangent both, I start them with 1s. But then this guy, the inverse secant, has this extra x multiplied in, and the x's kind of stay together. You might think of the derivative of what's inside here as popping out under the radical, but that's not a real good way. Anyway, those are the 3 basic ones. Now, here are the other 3. I'm not going to prove them, but, you know, it wouldn't be too hard to go through the same steps that I just went through. But I think you'll be not surprised, maybe surprised, but it's not bad. The derivative of the inverse cosine couldn't be much easier. Minus 1 over the square root of 1 minus x squared. The derivative of, maybe surprising, the derivative of the inverse cotangent. See, I'm writing all my co-functions on the right. The derivative of inverse cosine, inverse cotangent, inverse cosecant. And what's the answer? It's the negative of 1 over 1 plus x squared. I bet everybody can guess the answer to this one. Yep. Minus 1 over x square root of x squared minus 1. Why doesn't the book write it this way? I have no idea. It makes perfectly good sense. All the original functions are on the left. The co-functions are on the right. They are exactly the same except the co-functions have minuses in the derivatives. Not too hard to memorize. So you really only have to memorize the basic 3. And I do recommend memorizing these guys. They will come in handy, especially in Calculus 2. Okay, let's look at a few examples. Now, the good news is you do not have to, at least the good news for now, you don't have to go through any of this. This is good for you to go through to see where this comes from, mainly because we're going to use this argument again and again this semester, and it helps if you've seen it before. This idea with inverse functions of starting with the original equation involving an inverse function and then zapping that equation by hitting both sides by the function that undoes it. So we did secant on both sides of this equation to undo the inverse secant. So in general, if you've got an inverse function and you set that equal to y, then you're going to go f of f inverse of x equals f of y. And on the left, you're going to get x. So x equals f of y. So you can undo your inverse function by hitting both sides with the anti-function f and get this equation and then do implicit differentiation on that. So we'll see that again, in fact, in a couple of days. Anyway, let's look at some examples where all you have to know is this table right here. Okay, so we're going to assume that everybody has duly memorized that. Well, you don't have to memorize it instantly, but at least for the exam you should have it memorized. It'd probably be a good idea to have it memorized for the quiz. All right, so let's do an example where we're trying to figure out something like what is the derivative of the inverse tangent of x squared. Now you can go crazy trying to do this with thinking, oh, this is a power, I can bring it down. No, no, remember this power does not mean to the negative 1 power. It does not mean 1 over tangent. It means the inverse tangent, the arctangent. So how do I take the derivative of the inverse tangent? Well, I've got a formula for it. The formula says 1 over 1 plus x squared, 1 over 1 plus the argument squared, whatever you're plugging in squared. So the answer is 1 over whatever I'm plugging in, which is x squared, squared. But the chain rule says, wait a minute, what you're plugging in is not x. So you got to multiply by the derivative of what's inside. That's not too bad. 2x. So, final answer, 2x over 1 plus x to the fourth. All right, end of problem. Not too bad. Let's try another one. How about f prime of theta, where f of theta is equal to the arc sine of the square root of sine theta. Now, I didn't make this up. This is actually a textbook problem, one that I'm not going to assign, but I could have. It's not that bad. How do we calculate f prime of theta? What is the derivative? Well, you got to remember, of course, the arc sine means the inverse sine, just another name for it. So what is the derivative of the inverse sine of anything? The answer is the derivative of the inverse sine of anything is 1 over the square root of 1 minus that anything squared. Remember, here it is. Inverse sine derivative is 1 over the square root of 1 minus the argument squared. The thing you're plugging into the function squared. And what am I plugging into this function? Well, none other than the square root of sine theta. So I get to square the square root of sine theta. Well, we all know what that's going to be. That's not going to be too hard. Okay, so that is the derivative of the inverse sine, almost, except the chain rule says, wait a minute, that's not theta in there. That's not the independent variable. That's some horrible function of theta. So we got to multiply by the derivative of what's inside. How do I take the derivative of the square root of the sine of theta? Well, that's, remember, the sine of theta to the 1/2 power. So the derivative of anything to the 1/2 power is 1/2 times that anything to the minus 1/2. Almost, because again, what's inside here is not the independent variable. It's not theta. Therefore, the chain rule comes out again and says, you got to multiply by the derivative of what's inside there. So that's going to give us a factor of cosine theta. Okay, so let's simplify this a little bit. Obviously, the denominator simplifies to square root of 1 minus sine theta squared. So that's sine squared theta. Ooh, that's looking pretty good. I didn't know that was going to happen. And then we have a 1/2. I can put the 2 down here. Anything else in the numerator? Yeah, I got a cosine up there. And I've got a sine theta to the negative 1/2. That means 1 over the square root of sine theta. Okay, but I've seen 1 minus sine squared before. That's an identity that all of you should know, because sine squared plus cosine squared of anything equals 1. And therefore, 1 minus sine squared is cosine squared. So this is cosine theta, I lost the theta there, divided by 2 times the square root of 1 minus sine squared is exactly cosine squared times the square root of sine theta. So this actually is simplifying really nicely. This simplifies down to cosine theta divided by 2 square root of sine theta. Okay, now the question that everybody wants to know. If you left your answer in this form on a test, would you lose points? The answer is you'd probably lose 1 point. Yes, 1 point. Because this is so obvious. It's just begging for simplification. If you didn't see it, or you didn't feel like doing it, which I might not feel like doing on a test, you just pay the price. 1 point is not going to kill you. It's not going to make the difference between an A and a B. So you could write that off if you wanted to. In fact, I recommend not worrying at all about simplifying. Keep your eyes on the big picture. Don't worry about don't sweat the little things like simplifying. I'm going to be taking off big points if you don't understand how to take the derivative in the first place. What do you do to take the derivative of the inverse sine of something? Well, you have to remember the formula. 1 over the square root of 1 minus whatever squared. And then you've got to use the chain rule correctly. So doing that is worth 99% of the points. Okay, final example. Let's do this one. Again, a nasty one. What is the derivative of g, where g of x is the square root of x squared minus 1 times the inverse secant of x? And we're looking for g prime. Well, whenever I've helped you in the last few days, anybody who's been helped, the first thing I ask them is, what are you dealing with? What kind of thing is this? Look at it as if you were the big executive. You don't want to micromanage the problem. So you don't want to think about what's the derivative of the inverse secant, or what's the derivative of the square root, or what's the derivative of x squared minus 1, or do I use the chain rule here? No, do not even go there. You want to look at the big picture and say, what are you dealing with here? What kind of thing is this? What operation is being performed? Looking at it from the boss's point of view. From the boss's point of view, the boss sees two things multiplied together. The boss does not focus on what those things are. The boss sees two things being multiplied together. And so we say, how do you take the derivative of two things being multiplied together? Answer is the product rule. So at this point, you have no choice. You must use the product rule. So the answer is the first times the derivative of the second. I'm just going to write it that way. The derivative with respect to x, because x in this problem is the independent variable. The derivative of the second plus the second times the derivative with respect to x of the first, x squared plus 1, square root of x squared plus 1, or minus 1, sorry. Okay, how do we do this? Well, square root of x squared minus 1 is no problem. Neither is the derivative of the inverse secant, because we've got that memorized, or you will. The answer is 1 over x square root of x squared minus 1. Believe it? Let's check. Derivative of the inverse secant, right over here. 1 over x square root of x squared minus 1. All right. So that is the first times derivative of the second, plus the inverse secant times the derivative of that. What is that? Well, that's x squared minus 1 to the 1/2 power. We all know that. So the derivative is just going to be by the power rule, 1/2 x squared minus 1 to the 1/2 minus 1, which of course is minus 1/2. But the chain rule pops out and says, wait a minute, this is not x. It's a function of x, so you got to multiply by the derivative of what's inside there. And that's not bad at all. That's 2x. So now we just have to simplify. Well, look at this. This is pretty nice. Here's the square root of x squared minus 1 multiplied by something that's got an x square root of x squared minus 1 in the denominator. So these two guys are going to cancel, and you're just going to be left with, in the first term, 1 over x. Not bad. And then this guy is going to be staying there, and not much I can do about that, inverse secant. But the 1/2 is going to cancel the 2, and so I've got this x, and I'm going to go ahead and put this in the denominator as a radical. So this is square root of x squared minus 1. And that's it. I would leave it at that. I don't see anything better that you can do. I'm certainly not going to get a common denominator or put these together. That's pointless. So this is a perfectly good answer. You're done. And that's it for now. See you later.